Welcome to MEI Mechanics. We're on the topic of dimensional analysis, and this is video 1.2, dimensional consistency. So just a very quick reminder that we found that in mechanics any quantity that we're dealing with can have its dimensions written in terms of the three fundamental dimensions of mass, length and time. And one really important idea then is that if we're ever adding two quantities together or subtracting or equating two things, saying one thing is the same as another, then they must have the same dimensions, otherwise it doesn't make any sense. And that can be really helpful when we're analysing a formula, because we can tell if it's dimensionally consistent that at least it's a feasible formula, whereas if someone gives you a formula where there's an inconsistency in the dimensions, then you can rule that out as being a possibility. So for example, this formula here, could this be correct? We're going to assume throughout this that symbols have their usual meaning. So this V, we're assuming this is volume, so that has dimensions of L cubed. And then this formula here you may well recognize as the volume of a cone. So we should find, if we look at that, in fact we can quite easily see this has also got dimensions of L cubed, because we have an L squared, an L, and then a third pi are both dimensionless. So we have L cubed equals L cubed plus, and then we have this term here. This is the one that we need to pay attention to. This is just a number times a length. Alright, so we've got inconsistency here. We can't add these two things together because they have different dimensions. So no, that formula cannot be correct. So now we've got three more formulae, and we're going to test each one of these in the same way to see if it could be valid. Starting with this one, Fd equals mv minus mu. Now, we know the dimensions of force are m L t to the minus 2. And then that's being multiplied by a distance which has dimensions of L. On the right hand side, well, both these terms clearly have the same dimensions because they're both a mass times a velocity. So that's m times velocity, which is an L over t, so lt to the minus 1. So if we look at this both sides of this, could that be consistent? Well, this will simplify down to ml squared t to the minus 2. This is ml t to the minus 1. So both L and t will have a different index in the end there. So no, that's inconsistent. So that could not possibly be a valid formula. What about this one? Well, on the right hand side we've got the same as what we had above. So we've got ml t to the minus 1. On the left we've now got a force times a time. Now does that make a difference? So force is ml t to the minus 2 multiplied by a time. So that t to the minus 2 times a t will simplify to t to the minus 1. And so yes, it is consistent with this right hand side. So yes, that is a possible formula. This one here, Fd, well, we had that earlier as well. mlt to the minus 2 times L, which is ml squared t to the minus 2. And now here we've got a half. Well, half is dimensionless. Then we've got a mass m and v squared. So that is a velocity, L t to the minus 1 all squared. And when we deal with that bracket, we have m L squared t to the minus 2, which is the same dimensions we have on the left. So yes, that is also a valid formula. So it's nice to know that the formula that we've been using, like these two here, are consistent, but if we try to make one up, chances are it's going to be inconsistent. So this is a very, very powerful technique in terms of analysing formulae. So that concludes video 1.2, dimensional consistency. The next video will be 1.3, determining indices in a proposed formula.